Welcome back, guys. In this lecture we will design lag compensator. So before going to design the lag compensator, let us see the procedure for designing the lag compensator. This is lecture number 6 of unit 4. So in this process, so we don't have already said that the regions of border plot, in that region 1 gives the steady state error significance. So first initially in step 1 we choose a suitable value of k for uncompensated system. So by the given steady state specific error, if the steady state specific error may be kv, kp or ka, so basic upon that we'll find the k value. After finding the k value, we'll get a transfer function. For that transfer function, you draw this border plot. In the step 2, after drawing the border plot, you have to find the phase margin, right? After finding the phase margin, see that the phase margin will satisfy with our desired thing. So if the phase margin doesn't satisfy the desired thing, and we'll find a new phase margin, that is phi n equal to gamma n equal to f t plus theta. Now in this, after finding this, we'll find the frequency for this new gain phase margin, that is called phi GCN. This is a new gain crossover frequency for given for desired for a new phase margin. Okay. So after finding this, we'll have a procedure to find beta value. That is, if you see carefully, there will be a frequency at which this new gain crossover frequency, that is called omega GCN. Okay. With that omega GCN, from the border plot, we'll find the magnitude at which this gain crossover frequency. For this phase crossover frequency, we'll have a gain crossover frequency. On that frequency, we'll find the magnitude that is AGCN. Now, a lag compensator procedure is to attenuate something called to get the desired thing. That is this the formula. So we find this formula beta value. So as you know that for design thing, we need to know the values of beta and t. So from this, after getting beta, so we'll find transfer function by this form. Okay. So we choose the 0 of the lag compensator. So as you know that the lag compensator have a pole near to origin and a 0 far away from the origin. So we approximately will take ZC as omega GC by 10. Okay. And from this equation we'll find t value. After getting t value, we'll find pole value. Okay. So the pole value is almost 1 by beta t. This beta is almost 10. So we'll get more than 1, and t value for this we'll get pole very near to origin and 0 far away from the origin. Okay. So we'll find the transfer function by this form also. After getting the transfer function, just we'll club that in the overall transfer function. This overall function, we know that beta gives attenuation factor, so we introduce 1 by beta as amplifying thing to rectify the attenuation thing. After getting the overall transfer function, we'll check the phase margin. So here, without drawing additional border plot, a simple method is that we find the phase of this. Okay, with this phase of this, substituting omega value equal to gain crossover frequency, we'll get phase value. For this phase value, we'll get the new gain crossover, new phase margin for this obtained open loop phase of the system. So if omega naught is satisfying the desired specifications, that is phase margin, we'll stop the process of designing. If it does not satisfy, we just process from the fourth. We'll just form the lead compensator. We just follow from fourth also. Okay, this is about the procedure of lag compensator. So let us see with an example how to design a lag compensator. So to explain that, I have given a game with an example. So this is our system. For this system, they are asking you to design a lag compensator with a phase margin of 40 degrees and a gain margin of 10 dB and kV equal to 5 degrees. So this phase margin and gain margin will give the transient specification, and this is a steady state error specification. So the design thing, what we'll do is, we just go to the step 1. The step 1 gives us calculating calculating k value. So for this we have kv equal to 5 second inverse. So by this we have limit s tends to 0, s of g of s. Substitute this here. So limit s tends to 0, s into k by s plus 1, 0.5 s plus 1. So if you substitute these are all values equal to 5, right? So if you substitute s equal to 0, this value become k by 0 plus 1 and 0 plus 1. So it is equal to 4. Eventually obtain k equal to 5 value. Okay. So you got k equal to 5 value. You got k equal to 5, right? Now step 2 is to design a border plot for g of s. Okay, since you got k equal to 5, you substitute this in this here. So I'll get 5 by s into s plus 1, 0.5 s plus 1. So before going to do the border plot, what you have to do is you have to transfer whole this thing into 1 plus st form. Okay, so g of s equal to is 5 by s into 1 plus s plus 1 plus 0.5 s. Now what we will do is we substitute s equal to j omega here. So we'll get put s equal to j omega. So finally we'll get j omega 1 plus j omega, and this is in 1 st form. So 1 plus j omega by 2. Okay. Now from this we have the two corner frequencies, that is omega c1. From this we have 1 radians per second as a one corner frequency, and omega c2 equal to 2 radians per second. So these are the two corner frequency. For now we have to do the magnitude plot. So for the magnitude plot we have something called term values. So for the magnitude plot, what we'll do is, so we'll have a term value. So we have a corner frequency, and we have a slope for the each independent term, and we have change in slope. Okay. So initial term is, this is a 5 by j omega is a first term. It doesn't have any corner frequency, and the slope of the term is minus 20 since it has 0 at origin. And then the second term is, so 1 by 1 plus j omega is the second term, which has a corner frequency omega c1 equal to 1 radians per second. And this thing is also a pole, so we have a minus 20 dB, and there is a change in slope, so it's minus 20 to 20, that is minus 40. And after that we have another term j omega by t, so we have omega c2 equal to 2 radians per second, and this also have the minus 20 dB, and there is a change in slope from minus 40 to, so there's 60 dB. So we have obtained for this form. So this is the magnitude term. So now we have to find the magnitude at different frequencies, right? So to do that, we have to choose the low corner frequency. That is, choose lower frequency omega less than c1. So this is at omega c1 equal to 1. So I choose omega l equal to less than 1. This is 0.1 radians per second. And a high frequency that is greater than omega c, so I'll take 10 radians per second. Okay. Now the magnitude A at omega equal to omega L, A equal to 20 log 5 by j omega. Substitute omega is equal to omega L, that is 0.1. So I obtained this value about something called 34 dB. Okay. This I already calculated just to conceive time and doing straightly. Now at omega equal to omega c1, I got A equal to 20 log 5 by omega c1 is 1. So I obtain 14 dB. Now at omega equal to omega c2, now A equal to, here the things change. So there is a change in slope. Okay, from this term to this term there is no change. From this term to this term there is a change of minus 20 dB. So change in slope from omega c1 to omega c2 into log of omega c2 by omega c1 plus magnitude at omega equal to omega c1. So there is a change in of minus 40 into log of omega c2 is 2 by 1, so plus 14. So the value of this complete thing is, I got 2 dB approximate value. Okay, so these are the approximate value I got. Just now at omega equal to omega h, same, there is a change in slope, that is minus 60 into log of omega h by omega c2. Omega h value is 10 by 2 plus a at omega equal to c2, that is 2. So we have this value of minus 40 dB. Okay, so this is the value at different frequency. This is the frequency at different frequency. We have three values. This is the magnitude values, and now phase values. So how can I find that phase values means? So the phase value phi equal to, so we have the transfer function g of j omega equal to phi by j omega 1 plus omega by 2. The phase value here is, since numerator doesn't have any frequency terms, denominator we have full at origin, so straight away minus 90 minus tan inverse of omega minus tan inverse of imaginary value omega by 2. Okay, so real value is 1, so don't bother about that. Now for different frequencies we have to find phases, right? For different frequency I'm choosing omega value omega 1.5 and 1, 2, 5, 10, and I also have 100, interest of taking 100. So for different values I already chosen. For substitute omega for different phases, for omega equal to 0.1 I got a phase of minus 98.5, for minus 30, and this is minus 161, and this is minus 198, and this is 236, and this is 252, and this is 268. So I just calculated before. Now after updating the phase values and after obtaining the magnitude values, the next step is to design the we need to plot Bode plot with the same log frequency values. Okay, so this is the Bode plot, right? So for omega equal to 0.1 I obtained something at point magnitude value 34 dB. So the y-axis I took, this is the magnitude in dB. So for a different, I already plotted these. Okay, so I got some values. So at omega equal to corner frequency 1 I got 14 dB, so I plotted that. So here I j is 20, unit value is 20, so each division has 2 units. Okay, so at corner frequency 2 I got 2 dB. At corner frequency at 10 I got minus 40. So I got magnitude plot. So this is the magnitude plot I obtained. So this is minus 20 dB per decade, and this is minus 40 from here to here, infinity, so minus 60 per dB. Okay, this is the magnitude plot. Now for the phase plot, this is the phases value at 0.1. So in the left right side I take the phases thing. So this is the phase value in degree. Okay, so at omega equal to 0.1 I got minus 98 degrees. So 98 degrees is in between minus 90 to minus 120, obtained a point of view. Okay, so eventually at 0.5 I got some point at minus 130. So this may be at somewhere here. Okay, so I plotted all those things before only. Okay, for this I got the phase plot like this. Now our job is to find phase margin, right? Phase plot. So after getting the Bode plot, the next job is step 3, finding phase margin. Phase margin of uncompensated system. So from this we have to see the gain cause of frequency. So this is the gain cause of frequency at some point here. So if you draw this point, so draw this, I get omega gc equal to, so this is the 2 value, so I got 2.2 radians per second. For that I got phase 5 gc equal to minus 195. Okay, so for the phase margin of uncompensated system, so 5 gc is equal to minus 195, and the phase margin, the formula is 180 plus 5 gc. So that is, after substituting this, I got 15 degrees. Okay, so the thing is, our desired specification phi value is something, a value of 40 degrees. Okay, but I obtained minus 15 degrees. That means we have to improve the phase. Okay, to do that we go to, so obtained phi equal to minus 15 degrees, desired is 40 degrees, so lead lag compensator have to be done. Now in this process, if you find this phi is equal to 40 degrees, that means by this steady state error specification only our job is done. But now the phase margin is minus 15 degrees. Now we have to do the lag compensator. That is the key. Okay, so to do that we have to choose a suitable value of phase margin of compensator system. So that is step 4. Choose a suitable value for the phase margin of compensated. So we are really in lead compensator it is different. Now in this we will do alternatively margin of compensated system. Okay, this is called back engineering. So in that we have desired ft equal to 40 degrees, so that new gain cause of frequency, new phase margin is 5d plus eta. So by this 40 plus, so E is called additional lag, phase lag, so that is, we'll take 5 degrees. So new phase margin is of something called 45 degrees. Okay, now with this new phase margin we'll find a new frequency at this new phase margin. How we'll find that? We have same formula. So step 5 is now determining the new gain cause of frequency. New gain cause of frequency for this phase margin. So for that phase margin we have phi n equal to 180 degrees plus 5 GCN. Now from this we find 5 GCN equal to phi n minus 180. So I obtained phi n equal to 45 degrees minus 180. So I obtained phase at new gain cause of frequency is minus 35. Now to find the gain cause of frequency we use the Bode plot which we drawn before. Now the phi n will obtain where means, so this is the new gain crossover phase, that is phi n. So that is so here minus 120. So each division is 3. 3 plus 5 into 3 is 15. Minus 120 plus 15 is equal to 5 GCN equal to minus 135 degrees. Okay. Now at this phase, what is the frequency we have to see? So if we plot this, so I obtained a value of so near to 0.5. Okay. So I'm just interested to take this to the equal point. So my new gain cos of frequency omega GC equal to 0.5 radians per second. Okay, so this is old cos of frequency. For the designed lag compensator, the new gain cos of frequency is 0.5 radians per second. Okay, now at this gain cos of frequency, we have to find the magnitude which had to be attenuated by the lag compensator. So that is the main thing. So after finding this 5G, so by Bode plot, by Bode phase plot, we obtain omega GCN equal to 0.5 radians per second for omega 5 GCN. Okay, after finding omega GCN, so now what we have to do is we have to find the parameter beta. Okay, so step 6 is finding the parameter beta. So for the lag compensator, we have the transfer function GC of S equal to beta into 1 plus ST by 1 plus S beta T. Now our job is to find beta and T value. So to find this beta value, parameter beta, so we obtained 5 new gain cos of frequency 0.5. We have to find from the Bode plot again magnitude at omega GCN. So the magnitude at omega GCN, if you see, I have got something 20 degrees. Okay, this is called AGCN. So magnitude of at a new gain cross of frequency, I nominated it as AGCN. So that is 20 dB. So magnitude at omega that is AGCN equal to 20 dB. Now the lag compensator, so the lag compensator have to attenuate the AGC. So the lag compensator magnitude, if you go to the feedback, this is the lag compensator total attenuate value. We have to equate to minus 20. So from this equation, if you substitute further, I get a log of 1 by beta equal to minus 1. So if you further do, so I'll beta equal to 1.1. So beta obtain 10 value. Okay. So this is a beta value. So if you do some math here, I'll obtain the beta value 10, which is greater than 1. Okay. So after getting the beta value, the things gets easy. So after getting the beta value, the things get simplified. So now we have to find step 7, determining the lag compensator. So from these we have the lag compensator like this. Okay, pole at origin, near to origin. This is the important thing here, and 0 far away from there. So 0 of the compensator is approximated as is placed at a frequency 1/10, okay, 1/10 at omega GCN. So I'll give ZC equal to, so we have 1 by T, that is omega GCN by 10. So obtain omega GCN as 0.5 by 10. So obtain the compensated 0 at 0.05. Okay, so we have formula for pole PC equal to 1 by beta T. So we have beta value 10 and T value. From this equation we can find T equal to 1 by ZC. So obtained, if we substitute this here 20, so we substitute this T here, so obtained PC equal to 0.005. okay, so this is the pole 0 location of the compensated system. So now the thing is, we have to final transfer function of compensated system, though that is GC of S equal to S plus 1 by T by S plus 1 by beta T. So if we should do so other thing, so 1 beta equal to 1 by ST by 1 plus S beta T. So obtained B 10 into 1 plus T value is 20 by 1 plus 200. So now the steps 8 is, this is obtained the transfer function of the compensated system. Now we have to include it in open loop system, so whether it is suitable to design. So we had 1 by beta. So obtain why we have 1 by beta, because beta is the attenuation factor. So this is the compensated system and this is the open loop system. So G naught of S, I'll get, we do 1 by beta into B, so 1 plus S 20 by 1 plus S 200 into 5 by J omega into 1 plus J omega plus 1 plus omega by T. So if we further do this, we obtain G naught of it. So 1 plus S equal to J omega, so 20 J omega by 1 plus 200 J omega into 5 by J omega plus 1 plus J omega. So this is what the overall compensated system. Okay, this is overall compensated system. Now to check, now step 9 is to check this table, verify the design. How we'll verify the design is, we have to find the overall phase margin, which should be approximately or equal to desired phase margin. To check that, we have to find the phase of this, that is phi equal to phi of gain phi of new gain cost over open loop gain cost of frequency. What is the phase I can do from this here is, so the numerator having the term, so for that tan inverse of 20 omega, immediately have a denominator minus 90 minus tan inverse of omega minus tan inverse of omega by 2 minus tan inverse of 200 J omega. Now for where we have to check this at omega equal to omega GC. So that is omega GC is 0.5. If we substitute this here, I substitute omega equal to omega GC equal to 0.5 here, I obtained 5 GC naught value of minus 135.73. Now the phase margin is open loop system 180 plus 5 GC. So I obtained a value of 44.27, which is approximately a greater than desired thing. So now the design is accepted. So just go through in detail. So we didn't do any that big thing. Only we just did what we did is we have first find k value. For obtained k value, we design the border plot. For that border plot, we gain phase margin. After getting the phase margin, we have assumed the new gain phase margin for our desired thing. Why this we increase means, so if the design is not accepted, we have to increase again. Okay. So for this, I obtained a new gauge cost of frequency, new gauge phase. For this phase, we'll find from the order plot new gain cost of frequency. For this gain cost of frequency, we have the magnitude that lag compensator will introduce in the original system to attenuate this thing to meet that phase margin. Okay, that is the thing. So for that, we obtain the beta value. For that beta value, obtain lag compensator by knowing D and beta value. So after doing this, we included this here. To check the stability, we just simply, without doing additional border plot, we check that phase at that gain cost of frequency, and we make sure to know that is real to the desired phase margin. Okay, after we have accumulated this, if it is now this is near to a rate, so 40 actually desired, but it's more than 40, but it is near to 40, so we'll accept this. Okay, so this is about the lag compensator. So the next video I'll give a lead and lag compensator design. Thank you guys.